Santi and Giulia, I think that we can start. So a few technical details. Let me remind you that if you have problems with the streaming now, with Meet, the seminar is also streamed on the Facebook and YouTube channels of the observatory. Please mute your microphone, turn off the camera, and we'll have the questions at the end of the seminar by Giulia. So let me give the microphone to Santi, who is going to be the chair of this session.
Okay, so it is a pleasure to introduce Giulia De Somma to this seminar. A few words about her. She got the bachelor thesis in 2013 with the supervision of Massimo Capaccioli, with the thesis about the study of the luminosity function of globular cluster in a galaxy. After she got the master thesis with Professor Paolillo with the luminosity function but X-ray binary. So the only things in common is the luminosity function, but the objects were completely different. And since 2018, she started her doctoral fellowship with the supervision of Marcella Marconi and Professor Capozziello. And the field of her thesis concerned the development of an updated and exhaustive theoretical framework for pulsating variable, in particular classical Cepheids. And today I think that she will talk about this. Let me conclude saying that Giulia is maybe one of the most hard workers and fast speakers that I ever met in my career. So please enjoy her talk.
Okay. Just a moment. Can you see my slides?
Not yet.
Not yet, actually.
No. Now?
No. What browser are you using? Because today in another seminar there was a problem.
No, we already made some tests.
No, I think that
so
now
it just needs some time.
Okay.
It takes some time. Okay, that's okay, Giulia. And remember to hide the...
Yes. Thank you, Michele and Santi, for inviting me to speak at this seminar and for introducing me. Like Santi said, I'm Giulia De Somma, a PhD student from Federico II University and Observatory of Naples. My PhD project is supervised by Salvatore Capozziello and mainly Marcella Marconi. So today I will talk to you about the work I have been doing with her and the Stellar Group of Naples. A good portion of the work has already been completed, and I'm still working on a few things, and I hope to defend my thesis in May. The main topic of my PhD project is the development of an updated theoretical scenario self-consistent with the stellar modeling for classical Cepheid stars. This is the outline of my presentation. I will start by describing what classical Cepheids are and the several scientific aspects for which classical Cepheids are very powerful astronomical objects, focusing on two aspects: the use of classical Cepheids as primary distance indicators and the use of classical Cepheids as age indicators. Then I will talk about my theoretical project devoted to have a more solid theoretical scenario for classical Cepheids, building a new dataset of Cepheid pulsation models, varying for the first time all the relevant input parameters. Then I will show you our first models for galactic Cepheids, including and talk about the first period-luminosity-color, period-Wesenheit, and period-age-color relations in the Gaia filters, including also an application of this relation to a Gaia DR2 Cepheid sample. Finally, I will discuss my current conclusions and possible future developments. Classical Cepheids are luminous pulsating variable stars with masses between 3 and 13 solar masses, periods between about 1 and 100 days, and visual magnitude between -2 and -7, which lie at a pulsation instability strip. These stars cross the stability strip 3 times. The first time, called the first crossing, occurs during the subgiant phase, but this phase is irrelevant from an observational point of view due to the very short evolutionary time scale. The other 2 times, called the second and third crossings, are the most significant thanks to their longer evolutionary time scale. These crossings occur during the so-called blue loop phase of the HR diagram that corresponds to the central helium burning of intermediate and massive stars. These mass stars don't ignite helium with the flash, but do so quietly and then evolve in this blue expansion that is called the blue loop. It's important to remember that this phase is one of the most delicate phases of stellar evolution. Classical Cepheids and classical pulsating stars in general show a typical light curve in which we can see that the amplitude of the light curve decreases going from the optical to the near-infrared filters. So we see a decrease in the pulsation amplitude due to an increase of wavelength. But what are the scientific reasons that make these objects so relevant in both astrophysical and cosmological context? First of all, we know that thanks to characteristic and well-known correlation between pulsation period, luminosity, and distance, pulsation, luminosity, and color of these stars, these objects are the most important standard candles for the extragalactic distance scale. Yet there are some systematic effects that can affect this relation and consequently change the value of the distance of Cepheids and in turn the value of the Hubble constant. As the Hubble constant tension is one of the most fascinating issues in current astrophysical literature, they are very interesting objects, but we will come back on this point shortly. We also know that the Cepheids properties depend on metallicity, and so they can allow us to find metallicity gradients. And since their properties also depend on the helium content, if we have a survey of Cepheids for which the metallicity has already been defined using spectroscopy, they can also allow us to constrain the helium enrichment ratio from the pulsation properties. But classical Cepheids are also very important as benchmarks of stellar evolution because their properties depend on the assumed mass-luminosity relation. That means the different levels of luminosities correlate to several star masses. And since the masses depend on the on several phenomena that are related to non-standard physical phenomena like mass loss or convective overshooting or rotation, they can also help us to understand more about these phenomena. And finally, they can be used as age indicators and provide information on the stellar age distribution. For the rest of my presentation, I will concentrate on the first and last aspect. Let's start with the first aspect, the use of classical Cepheids as primary distance indicators. As I already mentioned, there is the relation between pulsation period, luminosity, and colors that makes these objects the most important standard candles for the extragalactic distance scale. Thanks to this relation, classical Cepheids are used to calibrating secondary distance indicators like supernova 1A or the globular cluster luminosity function and so on, with which the Hubble flow can be reached. And so it's clear that they are very important for constraining the extragalactic distance scale. Here you can see a plot that we will review again during this presentation that is the SHOES program by Riess. In their program, Riess et al. Use classical Cepheid relations to calibrate the absolute magnitude of supernova 1A and in turn reach the Hubble flow. From the stellar point of view, all the current estimates of the Hubble constant are based on this procedure. However, as the various ingredients entering the theoretical calibration of classical Cepheids can affect the value of the distance of Cepheids, they can also shed light on the residual systematics in the local determination of the Hubble constant. There has been a renewed interest in this topic in the last few years due to the debate on the so-called Hubble constant tension. By tension, we mean the unsolved discrepancy between the value of the constant derived by Riess using the Cepheid distance ladder and the value of the constant derived by the Planck collaboration based on the observations of the Planck satellite on the cosmic microwave background. I choose two plots that I consider very crucial for understanding the tension. The first is this plot made by Beaton et al., in which you can see that blue circles indicate the value of the constant derived by Riess using the secondary distance indicators calibrated on classical Cepheids, and red squares the value of the constant derived by using CMB modeling techniques as a function of the publication here. What's important to note from this plot is that since 2000, the two average values of the constant used to be close but with big errors. Instead, now the two average values of the constant are becoming more different and the error are reducing. So since 2000, we have seen a reduction in the errors and an increase of the difference between the two average values of the constant. And this stresses the effective presence of a tension. The other plot I choose is the more recent plot made by Verde et al. All the most relevant and recent estimates of the Hubble constant in the early and late universe are on this plot. In fact, in the upper panel, you can see measurements from the early universe, and so measurements obtained by using CMB modeling techniques. In the middle panel, measurements from the late universe, and then measurements obtained by using several kinds of local standard candles like Classical Cepheids, the tip of their giant branch, and so on. And in the bottom panel, measurements obtained by using, by combining primary and secondary distance indicators. I told you that the period-luminosity-color relations is a fundamental relation for classical Cepheids because it allows us to calibrate secondary distance indicators. But the problem in using these Cepheids as primary distance indicator is that this relation is affected, their use as primary distance indicators is affected by some residual systematic errors. These systematic errors are the intrinsic dispersion of the period-luminosity relation, the metallicity dependence of the period-luminosity relation, and the nonlinearity of the period-luminosity relation over the whole observed period range. Let's start with the intrinsic dispersion of the PL. The period luminosity has this intrinsic dispersion due to the finite width of the stability strip. This effect is usually neglected, but it's not irrelevant, as you can see in these two plots, in which in the plot on the right, you can see the typical evolutionary track of an intermediate mass star with the blue loop corresponding to the Cepheid evolutionary phase, and the intersection of this track with the blue and red edges of the stability strip. The green line represents the central value of the effective temperature. What I did was to evaluate the periods of the points at which the tracks and strips intercept. And what I found is that for the values of the stability strip at the same luminosity, we have different period values, and that this period difference is dependent on mass. In fact, I found for a 5 solar mass star a period difference of 1 day, and for an 11 solar mass star a period difference of 30 days. So it's not an irrelevant effect that we need to take into account and introduce a color term and derive a period-luminosity-color relations, but we will talk about this shortly. What's important to know is that this effect decreases going from the optical to the near-infrared filters, as you can see in this plot, in which the period luminosity for galactic and large Magellanic Cloud Cepheids are shown. So the reduction of the intrinsic dispersion of the PL is the first advantage in using mid or near-infrared filters. Another debated issue is the dependence of the period-luminosity relation coefficients on metallicity. This dependence would introduce another systematic effect when a universal PL is adopted to derive the distance of Cepheids in galaxies with a different chemical composition. In the plot on the left, you can see that both the slope and the intercept of the relation change when different metal abundances are adopted, and that the relations tend to become flatter at higher metallicity. This effect that is evident especially in the BV band reduces going from the optical to the near-infrared filters, as you can see in the plot on the right. And so the reduction of the metallicity dependence of the period-luminosity relation is another advantage in using mid or near-infrared filters. Another effect, over the past few years, several authors tried to estimate this effect, as you can see in this slide, in which they are all a few results, but you can note that the range for this estimate goes from minus 0.61 to plus 0.27, so it's a relevant effect. Despite this, there is still not yet a general consensus, and it is a highly debated open problem. Another effect we have is the nonlinearity of the PL over the rule observed period range. For a long time, the period-luminosity relation was considered linear in the period range from 1 to 100 days. However, since 2000, several investigations have indicated that the period-luminosity can be nonlinear in the B, VR, and also I band in the period range from 1 to 100 days. And here you can see one of the most relevant works on this topic, that is the work by Geo and Kambur. They simulated the period-luminosity, the nonlinear period-luminosity relation in the Large Magellanic Cloud using Macho and Oakley data, and they found evidence of a cutoff at 10 days, and they recognized the cause of this change in the slope of the PL in the interaction between the ionization front and the stellar photosphere that produce a lower luminosity from the PL. This effect, as the other two effects, reduce going from the optical to the near-infrared filters. So we understood that to reduce these effects, we can move from the optical to the near-infrared filters, and the theoretical simulations based on the pulsation models that I'm showing you here in this plot, in which you can see the period magnitude distribution of fundamental mode classical Cepheids at varying metallicity and photometric passbands, show that the intrinsic dispersion of the PL, the metallicity dependence of the PL, and the nonlinear effects of the PL reduce going from the optical to the near-infrared filters. But if you want to work in the optical band, the only way to do so is to introduce a color term and use the so-called Period-Wesenheit relation that is shown here for the B minus V color. The usefulness of this relation is that it is reddening free by definition, because the magnitude is replaced by the Wesenheit function, which includes a color term with a coefficient which is the exact ratio between the total and selective extinction. Traditionally, astronomers and also Riess et al. Use some combination of period-Wesenheit relations as primary distance indicators. Looking again at this plot that I showed you at the beginning of the presentation, the SHOES program by Riess, in their program, Riess et al. Use some combination of optical and near-infrared period-Wesenheit relation as primary distance indicators. The relation, the 0 point of the relation has to be geometric, so we can find it through parallaxes. And for the metallicity dependence, Riess used the NGC 4258, the galaxy with a maser, which has the metallicity much closer to the galaxies hosting supernova 1A observed by HST, respect to LMC, which is the galaxy traditionally used as anchor. Then once they calibrated this relation, they use this relation to find the distance of galaxies up to 30 megaparsec. And once they calibrated the supernova 1A with the Cepheids, they used the supernova 1A relation to reach the Hubble flow at about 100 megaparsec, right where the peculiar velocities became negligible, and it is possible to estimate the value of the constant by using the Hubble law. We have understood that to reduce the effects that I told you about, we can go from the optical to the near-infrared filters or use the Period-Wesenheit relation. But there are other systematic effects that we can reduce in that way and that are still outstanding, like the dependence of the extinction law on the environment, the dependence of the Period-Wesenheit relations on metal content, and the dependence of the period-luminosity, period-luminosity-color, period-Wesenheit relations on the mass-luminosity relation and different amounts on convection. So what we are doing theoretically is to try to quantify these systematic effects, and to do this we need Gaia's final data release. And here I'm focusing on the improvements afforded by the Gaia mission. In fact, the problem is that one of the causes of the tension could be the first step of the distance scale calibration, namely the geometrical parallax calibration of the coefficients of the PL. Maybe this part has to be reviewed. And as you can see in the plot on the right, in which in blue there is the Gaia DR1 data and in red the Gaia DR2 data, you can see that going from Gaia DR1 to Gaia DR2, the precision of the parallax measurements have strongly improved. As a result, as you can see in the plot on the left, that is a very recent plot that you can see in the official Gaia web page. It's very recent because it includes also results from early Gaia DR3. You can see that the third panel have the parallel relation derived from Gaia DR1 data. In the second panel, the PL relation derived from Gaia DR2 data, and in the first panel, the PL relation derived from early Gaia DR3. And you can note that going from Gaia DR1 to early Gaia DR3, the intrinsic dispersion of PL is strongly reduced. So we will expect that the Gaia final data release, the precision of the measurements of parallax from Gaia, the late Gaia data release will be so high that the error budgets related to the first step of distance scale calibration could be lowered 2.5%. That means that we can fix the first step of distance scale calibration and derive the distance of Cepheids with unparalleled precision. And we need also to have a more solid theoretical scenario. So based on an already tested theoretical project, we are building an updated data set of highly detailed Cepheid pulsation models. In fact, we are varying all the relevant input parameters. And so we not have to chosen to vary only the chemical composition, but also the mass-luminosity relation and the efficiency of super-adiabatic convection in the same data set for now. And in the next step, we want also to vary the helium content. So based by using the Stellingwer's dynamical code, the results from our dataset are light curves, instability strips, period radius and period mass radius relations, multi-band period-luminosity relations, and multi-band period-luminosity-color relations. We want a new dataset for different galaxies, and surely for LMC, SMC, Milky Way, but also Zwicky-18, which is one of the most metal-poor galaxies, and the spiral galaxy M31, which is a supermetallic galaxy. We choose to start our work deriving galactic Cepheids because, especially because the Gaia spacecraft work inside the Milky Way. We analyzed both fundamental and first overtone mode, and for each stellar mass, we choose 3 different values, 1.5, 1.7, 1.9 for the mixing length parameter that gives the efficiency of super-adiabatic convection, and 3 luminosity levels, a canonical luminosity levels, which means no rotation, no overshooting, and no mass loss, and 2 non-canonical luminosity levels that we obtained by increasing the canonical luminosity level by 0.2 dex and by 0.4 dex. After our analysis, we found around 360 stable pulsation models for the fundamental mode and around 40 pulsation models for the first overtone mode. I will now show you the results from this dataset that you can see in detail in the Astrophysical Journal. I'm starting by showing you the topology of the stability strip that we derived for the canonical mass-luminosity relation and the standard convective efficiency. As you can note, from the left to the right, you can see first overtone blue age, fundamental blue age, first overtone red age, and fundamental red age. If we increase the efficiency of super-adiabatic convection from 1.5 to 1.7, we find a narrower stability strip due to the quenching effect of convection on pulsation. And if we increase the values of the super-adiabatic convection from 1.7 to 1.9, we find a very narrow stability strip, and the first overtone mode disappears because at these values, the efficiency of convection is so high that the pulsation disappears. From our nonlinear models, we also obtained the radius curves for different effective temperatures, and from here, main radii, and from here, period radius and period mass radius relations. Here you can see the period radius relation that we obtained for both fundamental and first overtone mode at the canonical mass-luminosity relation, but changing the efficiency of super-adiabatic convection. And as we expected from previous results, the period radius relation does not vary considerably with the efficiency of super-adiabatic convection. Here instead, we fixed the efficiency of super-adiabatic convection and mass and changed the luminosity. And you can see that going from the canonical to the higher luminosity case, the relations tend to become flatter and the luminosity increases at a fixed mass. Then we performed a comparison between our theoretical period-radius relations and relations from literature, and we found a good agreement with Molinaro et al. And Galen et al. Period-radius relations, and we had a better agreement with Molinaro et al. At shorter periods and Galen et al. At longer periods. Here I'm showing you a part of the atlas of light and radial velocity curves that we have just produced. Here is an example of a part of the canonical mass-luminosity dataset, but we obtained this for all the assumptions we did. Dashed lines represent first order tone mode models and solid lines fundamental mode models. And on each light curves, we labeled the period in days, and on each radial velocity curves, the effective temperature in Kelvin. Here I'm showing you the effect of super-adiabatic convective efficiency on our light curves. And here we fixed the mass luminosity relation and changed the efficiency of super-adiabatic convection. And as you can note, as we increase the efficiency of super-adiabatic convection, the amplitudes of the light curves decrease and the morphology gets smoother. Here instead we fix the efficiency of convection and the mass and change the luminosity, and you can see that going from the canonical to the higher luminosity case, both the morphology and the amplitude of light curves slightly depend on the assumed mass luminosity relation. Our bolometric light curves can be converted into different photometric systems, and we choose to start deriving our bolometric light, converting our bolometric light curves into model atmospheres into the Gaia filters. So here you can see an example of the conversion of our bolometric light curves in G, GBP, and GRP, the filters of Gaia. And this provides the first theoretical Gaia light curves to the scientific community. From our light curves, we derived the mean magnitudes and colors that are the quantities used to derive the fundamental relations used in the extragalactic distance scale, the period-luminosity-color and period-Wesenheit relations. And here I'm showing you the coefficients that we obtained from for the period-luminosity-color relations on the left and period-Wesenheit relation on the right. And you can note that the main contribute came from the different assumptions of the mass-luminosity relation. Here we perform a comparison between our theoretical parallaxes based on period-Wesenheit relations in the Gaia filters and observed parallaxes taken from the recent catalog made by Pepi et al. And we investigated about the Gaia DR2 0-point offset. The Gaia 0-point offset is the offset found by several authors between the Gaia and the HST results. And we, taken as a reference the value estimated by Riess, we superimposed the value of the offset from our comparison on value by Riess. And we found that there is an offset, that this offset is consistent within uncertainties with the value estimated by Riess. And here you can see the comparison and our offset indicate also that the Gaia parallaxes have to be smaller in order to reconcile Gaia and HST result. Here is the comparison for the canonical mass luminosity relation and standard convective efficiency, but we obtained the same estimate for all the assumptions we did. It's important to note that a variation in parallax results in a variation in the value of the Hubble constant, and so it is crucial to quantify these effects to try to resolve the tension. Now I move on to the second scientific aspect that I want to discuss with you, the use of classical Cepheids as age indicators. Why can we say that Cepheids obey a period-age relation, and in how we can link a pulsation observable like the period to the age? I think that the plots I'm showing you here now are very clearly to understand this point. In fact, from the first plot, you can see that increasing the periods also increases the luminosities. But we know that classical Cepheids are associated with the blue loop phase of the HR diagram that predicts a mass luminosity relation. And so increasing the luminosity also increases the mass. But we know from stellar evolution that the evolutionary time scale are related to the mass, and that the mass is anticorrelated with the age, and we can see this anticorrelation from the third plot. And so if the period is related to the luminosity, which is related to mass, and thence related to the age, we can say that the periods are anticorrelated with the age, and as such that classical Cepheids obey a period-age relation. It's important to emphasize that Classical Cepheids offers a unique opportunity to estimate the age using the period-age relation from variable stars. The main advantages in using the period-age relation to estimate the Cepheid ages is that, one, the age estimates are based on an observable, the period, which is simple to measure because it is marginally affected by several systematic errors such as reddening, distance, and photometric calibration. And two, this relation can be applied to individual objects, while in general other methods can't be applied to individual objects. So it's clear that this method is very powerful, but what are the problems? The first problem is that, like the period luminosity was as the intrinsic dispersion because it was the projection of the instability strip on the color magnitude diagram, as such, also does the period-age relation. And for these reasons, for our work, we derived both period-age and period-age color relations. And the second problem is that this method is model-dependent, so we have all the uncertainties related to the intermediate mass star models. And for this reason, we needed the most up-to-date evolutionary and pulsation scenarios to conduct our research. For the evolutionary scenario, we adopted the last up-to-date version of the BUS IAC library, which is one of the most up-to-date stellar evolution model libraries. The physics in the library is updated, and it offers a wide samples of masses, metallicities, evolutionary times, and also the possibility to investigate the core convective overshooting during the previous hydrogen burning phase. For the pulsation scenario, we adopted the updated dataset of models that I have just shown you. And for the aim of this work that you can see in details in monthly notice, we adopted only a part of this dataset, and in particular, masses from solar masses from 4 to 11, two luminosity levels that corresponds to canonical and non-canonical mass evolutionary models, and two efficiency of super-adiabatic convection, 1.5 and 1.7. By combining evolutionary and pulsation scenarios, we found which masses are inside the stability strip and their corresponding ages. Then, by using the period luminosity mass temperature derived in our previous work, we derived the period of each combination of mass, luminosity, and effective temperature. And so that way we have the period and the age for each stellar model derived from the evolutionary models, and by performing a linear regression, the period-age relation. Here we study the dependence of the period-age relation of the assumed mass-luminosity relation, and as we expected, the period-age relation is affected by different assumptions of the mass-luminosity relation, and brighter mass-luminosity relation provide systematically all the ages. Instead, here we study the dependence of the efficiency of super-adiabatic convective efficiency, and we find that the P relation is not affected by the exact value of the efficiency of super-adiabatic convection, and as such, I will only present the results for alpha 1.5, only the results for alpha 1.5. Then we thought it was important to perform a comparison between our theoretical relations, our period-age theoretical relations, and the existing literature. Literature offers several theoretical relations, like the ones by Bono or Anderson, and also some semi-empirical relations, like the ones by Efremov, Sencina, Magnier, and you can see the comparison between our relations and these relations from the bottom panel of these plots, in which the shaded region represents the 1 sigma error on the relation, and you can see that in both canonical and non-canonical cases, the slope of the relation is the same, and when they are at the same periods, also the intercepts are very similar. What does the result mean in terms of age? So we can answer this from the upper panel of these plots, in which we derived the relative, to have a better, to quantify the agreement, we derived the relative age differences between our relations and these relations, and we found that there is a good agreement apart from Chekhov and the relation by Sencina, which is also the relation with the big error, for both canonical and non-canonical cases, and that the agreement increases going from the canonical to non-canonical cases, which is also the more probable on the basis of evolutionary considerations. As I already told you, the problem using the period age relation is that, like the period luminosity relation has an intrinsic dispersion, so also does the period age relation. So to overcome this problem, we decided to derive the period age color relation. Clearly, this relation depends on the choice of the photometric systems, and as for the previous work, we decided to start deriving the relation in the Gaia filters. So by using the Gaia band model light curves, mean magnitudes and colors derived in our previous work, we derived the first period age color relations in the Gaia filters. As the aim of this work was to derive the individual ages of galactic classical Cepheids with Gaia DR2 parallaxes, to test our relations, we applied the PA and PAC relations to the same sample that we used in the previous work, the sample made by Ripepi. And we derived, by using colors and periods reported in that work, we derived the individual ages for about 560 fundamental mode galactic classical Cepheids and 200 for overtone mode galactic classical Cepheids. Here you can see the age distribution of fundamental and first overtone mode galactic classical Cepheids, fundamental on the left, first overtone mode on the right. And as you can see, and as we expected, plot on the left, we obtained that for brighter ML relations, we obtained systematically all the ages, and in particular, the age peaks around 85 megayears for the canonical case and gets older by about 35 megayears for the brighter ML relation. For the fundamental first overtone mode plot on the right, we obtained that due to the masses and periods being smaller than F1s, the entire age distribution is concentrated towards older ages. The possibility to obtain the accurate and reliable age estimates for a large sample of galactic classical Cepheids give us the opportunity to perform an age homography of the galaxy and hence to properly trace the various portions of the Milky Way, in particular for young and intermediate ages. So, to estimate the age of the galactic classical Cepheids in function of their position on the galactic disk, we represented the galactic classical Cepheids with their coordinates, with their galactic coordinates, and estimated the ages by varying according to a logarithmic color bar scale with an ascending gradient from blue to red. We estimated the age, and we found that the predicted ages decrease towards the galactic centric distance, the galactic center, and that the oldest Cepheids are located at a larger galactocentric distance, and that for the same assumption on the mass-luminosity relation, first overtone mode Cepheids are systematically older than the F1s. Now, to conclude, we talked about the classical Cepheids as primary distance indicators and age indicators, and so stellar population tracers. We talked about my project, the updated dataset of evolution of stellar pulsation models, talked about the first theoretical period-luminosity-color, period-Wesenheit, period-age color relations in the Gaia filters, and including also an application of this relation to a Gaia DR2 database. And we can conclude that our models are successfully tested against Gaia DR2 and that classical Cepheids are excellent tracers of population 1 stars. But what do we have in mind for the future? For the future, we are developing different projects, and we plan to extend the present theoretical investigation to other initial chemical composition in order to properly account for the full metallicity distribution of galactic Cepheids and to allow the application of period-luminosity-color, period-Wesenheit, period-age, and period-age color relations to extragalactic sample. We plan to provide the period-luminosity-color, period-Wesenheit, and period-age color relations to other photometric systems like JWST, LSST, and so on, and to estimate the value of distances and the value of the Hubble constant as a function of the mass luminosity, the efficiency of super-adiabatic convection, and chemical composition, providing in that way a new theoretical calibration of the extragalactic distance scale. Thank you.
Thank you, Giulia, for this very complete overview about the modeling